Okay, so this second part of chapter 8 is, or of lesson 8 is actually building from scratch a fully connected neural network. And although we don't really see it in the lesson, the network is really built to process the MNIST data, which is the digits database. Remember, you're trying to look at 28 pixel by 28 pixel images of digits and then classify them with a number from 0 to 9. That's the output of the classifier. So what Jeremy's doing in this lesson is actually building a neural network to accomplish this. And the way he does it is he maps the images into an encoding, which he's chosen to use 50, a vector of length 50 for the encoding. So he's basically mapping a 28 by 20 image, which is really a two-dimensional array, which has 784 elements. So he's basically, you could also think of that 28 by 28 array as a 784 by 1 vector. So he's basically mapping that 784 by 1 vector into an encoding of a 50 by 1 vector, and that's the hidden layer. And then the hidden layer gets mapped to the output, which is simply a digit between, a digit from 0 to 9. All right. I'm trying to get to the next slide, but it's not obeying my command. This. Okay. Can everybody see that slide? That says overview.
Yes.
Is that being shared correctly?
Yes.
Thank you. Okay, so the first part of the lesson goes through normalization and initialization, which turns out to be really important because if you lose it, especially in a deep network, if you don't keep your weights within certain bounds, then the derivatives tend to blow up or go to 0, and then you have a problem. Most especially in a very deep network. This network it's basically the minimum thing that qualifies as a deep network. It has one hidden layer. So the normalization and initialization is designed to keep the mean and variance of the weights to being a standard normal distribution with mean of 0 and standard deviation of 1. So I'm going to just dive right into the notebook, because that's the best way. If you haven't done it already, then that's the next thing that you want to do to review this lesson. I'm trying to share the notebook. Am I sharing that?
Not yet.
Not sharing it. Okay. Let me stop sharing the PowerPoint and see if I can. Nope. Now I should be sharing the notebook. Can people see that?
Yes.
Okay, great. So I'm sharing notebook. It's called 02_fully connected. That's what we're covering. That is essentially lesson 8B. So you can either do it on your machine if you have that set up, or you can do it on Colab. And so I'm just going to go through that. Let me see. First of all, since I've already been through it, I'm going to restart the kernel. And then starting from scratch. All right, so let's go through. The first part of it is just to load the MNIST data with the digits and so on, and pre-process it by normalizing it in the standard way. So you can see so I'm going to do that, run. And you can see what that normalize function does. It basically just subtracts the mean and divides by the standard deviation. That's just a function to accomplish that. Okay, so these are the functions that we need. Now we're going to actually do it, get the MNIST data and put them in. And notice here that it's returning a tensor, because we need tensors. We need to work with tensors when we use PyTorch. So it's mapping the arrays, which are just NumPy arrays, into when you download the data, it comes in the form of NumPy arrays. So it's going to transform that into tensors. That's what this return map tensor line does. All right. So now let's do it. It takes a few seconds. This notebook is nice because none of the steps take very long. They only take like a few seconds each. So you can easily run through it. All right. So now we're going to compute that mean and standard deviation that we're going to need for the normalization. And there they are. And notice that since the the data itself is in the form of tensors, when you take mean and standard deviation, you're also going to get tensors. So that's what we got. Let's see. Oh, okay. So now we're going to normalize the data. Actually do it. And normalize the training data and the validation data. And notice that when we normalize the validation data, we have to do it using the mean and standard deviation of the training data. So when this function normalize, this is the first input is basically what you want normalized, and the second input is the mean, and the third input is the standard deviation that you want to use to do the normalization. So when we normalize the validation data, we have to use the mean and standard deviation of the training data. Any questions about that? Okay, so to do that, if I haven't already. Now we check that the mean and standard deviation of the normalized data are 0 and 1, as they should be, since they're normalized. And wait, get the data, deviation, normalize, and then check. There it is. So the mean is close to 0, and the standard deviation is 1, so that works as it should. The one thing question that I had is I'm expecting the mean to be 0 to machine precision, but which is what would happen if I were working in NumPy. But since I'm working with tensors, something gets lost. You don't get machine precision. You just get very close to 0. And in fact, Jeremy built this function to test that things are near 0, and he made the tolerance only 1 times 10 to the minus 3. So that's all he cares about, is that it's within 1 times 10 to the minus 3 of 0. So this is that function. And what happens is, with the way this function is built, is it basically throws an exception if it's not near 0. So if it is near 0, then it just doesn't do anything. And so if we see nothing after we run this, then we know that it passed the test. We could have constructed this in another way to actually give a message that it passed the test, but that would take more time. So anyway, so we do the test. It passes the test. Now we can look at the shape of the training data and put the number of rows and columns into variables n and m. And then for the output layer, we add 1 to the max of the train. Because remember, y train is going to be digits from 0 to 9. And so the maximum of that is 9. And the number of digits is actually 10, because we have 0 through 9. So that's why we add 1 here. C is basically the number of entries in that, the number of possibilities in y train. So now we see there's 50,000 rows. Those are examples. 784 columns, because we basically mapped the 28 by 28 array into a vector of length 28 squared equals 784. Does that make sense? Okay. And then the dimension of the hidden layer is is 50. That's what I was saying. Jeremy is basically mapping the 728 pixel array into a 50 into a vector of length 50. That's the encoding of the image. And the encoding is something that's hidden. We don't ever know what it actually means. PyTorch just fits for it and figures, the neural network just fits for it and figures it out. That's why it's called the hidden layer. The pixels mean something to us. If we take that 28 by 28 image, we can actually look at it and make some sense out of it, but you're not going to make any sense out of the 50 element encoding of that. That's the hidden layer. Okay, so now he's going to do the simplified timing initialization, which comes from that paper that he had us read, section 2.2 of delving deep into rectifiers or something like that. So the weights are being initialized to, okay, remember the weights are going to be an array of 728 by 50, 728 for the number of columns, the pixel data, and NH for the hidden layers. So we expect we're initializing it to an array of 728 by 50. And then we divide by the square root of the number of rows basically, because that's the average. When we do the average, we're gonna, no, I'm sorry. I don't remember why we're dividing by the square root of the number of rows. I'll leave that for later. And B1 is the column vector of the biases, and we always initialize that to 0. All right, and then W2, the second layer maps the hidden layer, the vector of length 50, to a single number, and so it's initialized to 50 by 1 vector of just basically Gaussian random numbers. That's what's happening too. We're initializing to random. We're basically doing random initialization. Okay, so I'll do that. And now let's check. The mean should be 0. Standard deviation should be 1 over the square root of m. Because if we did this, sorry, if we did W1, and if we didn't divide by the square root of m, then this would be a Gaussian distribution with mean 0 and standard deviation 1. We would expect its standard deviation to be 1. But because we're dividing by square root of m, the standard deviation, we expect it to be 1 over square root of m. So 1 over square root of m is 1 over square root of 784 is 1 over 28, which is 0.0357. That's what we're expecting. So we do that. We look at the mean and standard deviation, and they are close to what we expect, close to 0 and close to 0.0357. Then we use Jeremy's function to test that the mean is near 0 and the standard deviation is near 1 minus, that is, the standard deviation minus its expected value, minus 0.357, should be close to 0. That's what we're testing here. And since there's no complaints, that means the test was passed. Let's see. What else? Looking at the validation data, its mean and standard deviation, close to 0, close to 1. It's normalized, so it's normalized with, remember, with the training data. So we don't really expect it to be exactly close to 1 because it would have a different. If we normalized by its own mean and standard deviation, then we would expect it to be near 1. But since it looks like the training data has very similar mean to the validation data, because it is close to 0 and 1. Okay. Next, he defines the function that we need to implement a linear layer, which, remember, is just a matrix multiplied by the weights and then add the bias. That's the affine transformation that makes up a linear layer. So that's the function that implements it. Now we actually instantiate that function and run it and put its result into this thing called T. Remember, we have W1 and B1. We just initialized them, so they're defined. And now T is also defined. So let's look at T. We expect that it has a mean near 0 and standard deviation near 1, because that's what timing initialization is supposed to do. So we try it, and indeed it is. The mean is close to 0. The standard deviation is close to 1. Although the mean isn't as close to 0 as we might want it to be, though. It's almost 0.03. Okay, the next function we're going to need is a ReLU activation. And Jeremy has this really nice, succinct way of defining it. remember the ReLU is just basically 0 for x less than 0, and then it's x for x greater than 0. And you can implement that function cleverly in one line by x.clamp underscore min of 0, because we want to clamp the x less than 0 part to 0. So there it is. That's the definition. Now we actually use it, and since we have x valid, we have W1 and B1 initialized, we can run the linear layer and then run the ReLU on that. And so that's basically the next step in forward propagation. So, and that gets put into this variable t, and now we check that its mean and we check what its mean and standard deviation are, and they're not that great. I mean, the mean is close to 1/2, and the standard deviation is way different than 1. So this is where the first attempt we made at He initialization didn't include this factor of 2 that He included in the paper. And that's what we're going to do next. We're going to reinitialize with this improved version of the initialization to get a new initialized version of W1 with this factor of, the only difference is the factor of square root of 2 in the numerator. Now we just check the mean and standard deviation of W, that yes, they are. Yeah, we expect, remember the standard deviation should be square root of 2 over 784, which is 0.0505. I calculated that. And indeed, it's close. The standard deviation is close to that. And the mean is close, again, close to 0. So that's the new initialization. Yeah, hello? Someone had a comment? Hello? I'm hearing somebody in the background. Okay, so let's move on. Okay, so we checked that the mean and standard deviation are as they should be. And now we can check that the mean of the ReLU, the mean and standard deviation of the ReLU. And
hey, Joseph, I have a quick question there.
yeah, sure.
Why are we using X valid, even though we're kind of trying to train on this data, right? So shouldn't we be using X train? I mean, for the purpose of this experiment, I see no difference. But is there something that I'm missing?
No, I don't think you're missing anything. We could have done it with X train.
Okay.
Yeah. So I think he just picked X valid to do it with. Okay, so now we're going to run the ReLU. We're going to do the first 2 layers, the linear layer and followed by the ReLU, and looking at what we get. And we're getting that the mean is close to 1/2. The standard deviation is about 0.8, which is sort of close to 1, or at least it's closer to 1 than we saw before. That was 0.6. So we did get an improvement in the standard deviation. We're expecting it to be close to 1. Let's see. Now, since I guess what Jeremy does is, now that since we've implemented ourselves, we're now allowed to use it from PyTorch. So we're going to import this init part from the neural networks part of PyTorch, and it has its own special function for initializing called init.timing_normal, and then it does that. And he shows you how you can actually see what's in the function and so on. You can understand what fan in means and so on. So you can actually look at that. I won't stop there though. And then this is the documentation for timing normal. So you can actually investigate what that function does. In any case, we have just initialized with PyTorch, and now we can look at the mean and standard deviation and find that it's about the same as what we had with our own version. And again, Jeremy notices that although the standard deviation is close to 1, like it should be, the mean is closer to 1/2. And it turns out that, as Jeremy found out just by playing around with it, that's because you're using a ReLU, and the mean of a ReLU is 1/2. So let's see. This is just reviewing ourselves. The shape of W1 is 784 by 50. I think further on, let me just go through this next few steps. He's importing the rest of torch.nn and looking at the shape of the weights matrix in PyTorch. And he points out that it's in PyTorch, the only difference is that it takes the transpose of the weights matrix the way we think of it. So its weights matrix is 50 by 784. And we just have to remember that as we go on. You can look at the documentation of these things just with this double question mark, of these functions with these question marks. So I'll leave that. And then Jeremy comes up with this idea, let's revise the ReLU by subtracting a half from it, because then it will actually, then when you initialize it when you initialize your weights and then you form the ReLU layer, the idea is that now it's really going to have a mean close to 0 and a standard deviation close to 1. So let's try it. Revise ReLU function, same as the one before, except you subtract a half from it. And now, when you run this initialization, you do get, when you run the timing initialization, you revise ReLU function, you actually get a mean that's close to 0 and a standard deviation that's close to 1. So Jeremy's demonstrating that this idea of his that seems to work. Okay, the next thing he does is he combines the layers in series to create a model, because remember what you're doing is you're doing the first linear layer followed by a ReLU activation followed by the second linear layer. So the first linear layer maps the matrix to its encoding, to its vector of length 50. Hold on for a sec. I'm going to manage participants. I'm going to mute everyone if you have something to say.
Hey, Joseph, I have another question. Like, why do you know why the mean for the ReLU is 0.5? Is there any behind
well,
that?
if you look at the function, you know that it goes from 0 to 1 with slope of 1, or 0. Yeah, it's a triangle, right? And it goes from 0 to 1 with a slope of 1. If you take the mean of that, it's going to be a half.
But the ReLU is basically anything less than 0, truncates at 0, but the positive end is not clamped, right? It can go up to any amount. If it goes up to 1, then yes, I think the mean is 0.5, but there is no limit on the positive side, right? It's X.
Yes. Yes.
So why
okay.
is it?
I see your question. I'll have to think more about that. I'm going to take a note and I'll think about that and try to answer it later.
Yep.
But I see your point.
That sounds good. Okay.
Make a note. Okay, so going on, so he combines these layers to create the model that we want, and basically the model is mapping the, it maps the 28 by 28 array, first maps it into a 50 by 1 vector, that's the embedding, then you apply the ReLU, sorry, yeah, then you apply the ReLU on that, the ReLU activation on that, and then you map the result into a single number, and that's the second layer. Well, in this one it's the third layer, but it's the second linear layer. It's L2. So this function here, model, is basically just the forward propagation of our input data into an output, which is a number, which tells you which digit it is. All right, so now he says, okay, we've done this, we've defined our model, let's see how long it takes to run. So he runs it for 7 runs of 10 loops each. That's what he has set up. And we see that it takes, 13 milliseconds. Let me try that again. Doesn't seem right. No, it does seem right. So it's 10 milliseconds. Oh, that's the forward step. Okay, that's fine. Okay, the next thing you need for a neural network is a loss function. And in this case, he just defines the mean squared error. That is the value of the digit that you predicted minus the value of the true value of the digit. The sum of those squared for over all the examples. And that's what this function is, MSE. The In this case, the output is the prediction of the model. It's the model prediction for the digit, right? And the target, TARG, that's the true value of the digit. And so he constructed this function that simply takes the true value minus the target, squares it, and takes the mean over all of the examples. And that will be our mean squared error. And of course, we want to minimize that. So that's our loss function. It's not the right loss function for this problem, but it's simple. So that's what we'll do for now. The right loss function for this problem, since it's a classification problem, is a cross entropy loss. But just to make things simple, he's using this mean squared error for the loss. Because we're not trying to even train the model in this one. We're just trying to construct a model that works. Okay, so let's look at the model. We built this model right here. Let's apply the model to the validation data and look at the shape. So it's what we expected. The validation data has a length of 10,000, and the prediction should also have a length of 10,000. And there it is. The size of this tensor is 10,000 by 1. Now, let's see. I want to look at the truth values. That is y valid, its shape. And you notice that it's got a slightly different shape. It doesn't have the extra dimension there. So that's why Jeremy says here that we need to use squeeze in MSE to get rid of that trailing one, that trailing dimension. That's why we take output, which is the model output, dot squeeze of -1. That means remove the trailing one. So now output dot squeeze of -1 has the right shape to combine it, to be able to subtract targ from it. It will have this shape. Okay. Let's prove that. Cell below. Take this. I want model. Model of x valid. That's our out. Okay, I'm going to do that. Model of x valid dot squeeze of -1. Okay, we already know that this has a shape with a trailing 1, right? Now let's squeeze that last one out and check that the shape is what we expect it to be. Actually, okay, I'm going to put another cell below, and then I'm going to check its shape, that the shape is what we expect. In other words, that we effectively remove, by using this squeeze of -1, we effectively remove that trailing 1. And there it is. So now that thing in the function here, output dot squeeze of -1 is the right shape so that you can subtract targ from it. Because remember, targ has this shape of 10,000. Okay. So that explains this note that Jeremy made here. I'm not sure. I have to figure out what this does, but it's in there. It somehow takes the training tensor and forces it to be a float. I'm not sure. Maybe I'm not sure what this actually does. I'll have to look it up. If anybody knows, can you jump in and say?
To take the means, you need kind of a float value. You can't do it directly on the tensors. So that's why because you're going to finally in the MSE going to end up subtracting both of them and then take a mean.
Yes.
So that's why he's converting it to a float before he passes it in there. Otherwise, if you just pass in the tensors, you can't subtract and take a mean on that. The point is the mean can be taken only on float values.
Okay, but I thought I saw that it's still a tensor, because if I do type of by training, after having done that, I thought I saw that it was still a tensor. Yeah, it's still a torch tensor. So I'm not quite sure.
Can
I
you
understand.
run
Yes?
ytrain.float itself? If I'm not wrong, that's what I saw.
Oh, okay. But it's been converted, so it shouldn't matter. But let's try that. Okay, so y train dot float. Sorry.
It's a float of TensorFloat.
It's a TensorFloat.
Yeah.
Okay. Okay. But what's the difference between a TensorFloat and a normal tensor?
Initially, what was the value, the type of the Y train? Probably it was integer, something like that. And in your, when you compute the loss, it's probably expecting.
Oh, you're right. You're right. It turns it. Yeah, it's integers. That's why you need this. Thank you. Thank you. Yeah, because the Y train is integers between 0 and 9. And we want everything to be done in the MSE has to be a floating number. So that's why this is done. Convert tensor to floats because they were initially. Okay. Thank you so much. That's great. All right. So now we can run the model on the training set to get the predictions. Verify that the shape of the predictions this time is going to be 50,000 by 1 because the validation set was 10,000 by 1. Had 10,000 examples. The training set has 50,000 examples. All right. So now we can actually evaluate the loss function because we've constructed it. We've got the predictions. We've got the real. We've got the true values. So let's run the mean squared error, and it's 26. It's pretty high. But that's just one forward pass on the using randomly initialized weights. So the neural network's going to actually do a lot better than that eventually. Okay, so the next step is the backward pass. I have this part is hard to follow, but I'm going to get out of here for a second and just go to the PowerPoint where I do this. I'm going to share the PowerPoint now. Next page. I'll go back. I'll go one more page. So the backward pass is basically computing the gradients. The gradient of the loss function with respect to the parameters in your model. And the parameters are the weights and biases. So that's what eventually we need to do with the backward pass. And why are we doing that? We're trying to measure the sensitivity of the loss function to these parameters so that we can twiddle them and get parameters that make the loss function smaller. So if varying one of the weights makes the loss function, if varying it in the positive direction makes the loss function get bigger, then we want to vary it. Then we want to vary it in the negative direction instead, because that'll make the loss function smaller. So just in a general sense, that's what these gradients are measuring for us. They're telling us what the sensitivity of the loss function is to changes in its parameters. And the reason why we're doing that is because eventually we want to actually update those weights in a loop. We want to keep updating the weights until we make the loss function as small as we can. So that's what the backward pass is doing. Now, and to do that, we're basically this is a nice slide that comes from Jeremy's lecture. What is our network doing? It's mapping the input data X through a linear layer. Remember, that's W1 times X plus B. And then we're applying a ReLU activation on top of that. In other words, and of course, this linear layer is mapping the 728 element array into a 50 element embedding, right? Then we apply the ReLU to that 50 element embedding. And then we apply another linear transformation. Again, it's going to be W2 times the output of the ReLU plus B2, the bias is the second bias vector. So there's a second weights matrix W2 that multiplies the output of the ReLU and maps it into a single number. And it also, when you have all of this stuff, you can then compute the mean squared error. So there actually should be two errors here because you don't need y. You don't need mean squared error to compute y. There actually should be an arrow from lin2 directly to y hat, which is the estimate of that is the digit, the output. But also, when you have all these things, you can compute the mean squared error. So then the backward. Okay, so okay. Wait, I'm not sure why he says y hat is the mean squared error. Y hat should be the estimate of the digit. Anyway, that's a little confusing to me. I'm not sure why he wrote it that way. But anyway, when you have the mean squared error, the main thing to focus on here is that the mean squared error is a function of a function of a function of a function. That's what these brackets are doing. So the innermost part is the first linear layer, and then we take the ReLU of that, and then we take lin2 of that, and that's the mean squared error. So the mean squared error is this deep composite function. And the chain rule tells us that we can take the derivative of this function with respect to any of the parameters by using the chain rule. So what you'd actually do is you'd take the derivative of MSE with respect to lin2, that would be dy dx. If we wanted to take derivative of the MSE with respect to ReLU, we would do this. We would go dy dx, where y is this thing, x is lin2. X is ReLU. So dy d ReLU is dy d lin2 d lin2 d ReLU. That's what the chain rule would do for the first step. And then you might want to take then the next step would be to take the derivative of the mean squared error with respect to lin2, and then you'd have three terms. It would be dy dx, dy du, du dx, then you'd have dx dv, the third layer. So the chain rule is basically a product of derivatives, and you can use it to get the derivative of the mean squared error with respect to any of the parameters, by which I mean the elements of the W and B matrices, W1 matrix, W2 matrix, B1 vector, and B2 vector. The chain rule is the tool that allows you to get these derivatives, and that's going to be used in this backwards path. There is a nice, a nice paper that I have to read. I'm going to promise myself that I'm going to read it. I actually thought I would read it by today, but I didn't. It's this. I think it's a paper that Jeremy and Terence Parr made and published, and they just released version 3 or something just a couple days ago. So they fixed it or something, edited it. But anyway, I think it would be a great idea if you had time to go and read this thing. I think it's I don't know how long it is. Let me see. It might be just 30 pages or something. I actually printed it out, but I don't have it handy. Oh, there it is. Yeah, it is. I can tell you how many pages. Yeah, on the 2nd July is the latest revision, and it is 33 pages. So anyway, it might be a good read, because once you read that, you would really have a really good understanding of all of this backward path stuff. All right. Yeah.
Question?
Yes.
Yeah. By the way, do you go by Joe or Joseph?
Joseph.
Joseph. Thanks.
Yes.
Listen, what we were just looking at the math that you had put up that Jeremy had handwritten. Yeah, that's that one.
Yeah.
Was that when we think of that we're going to have 50 50 nodes? We're going to have a hidden layer with 50 how do we say that, nodes? Is that right?
I think so. Yeah.
Yeah. So when we say lin2, is that the linear function for the second node? I'm trying to put this together with you know, those diagrams that you see of, well, here's the input, and then here it goes to the hidden layer, and there's 50 of them, but it goes to all of them.
Yeah.
And sort of
I see your question. Okay, so let's think of this. Let's go through this part here. X is the input data, which is, you know, if it were the validation data, it would be a 10,000 by 728 array. Does that make sense? Right?
10,000. Yeah. Yep.
Yeah. Validation has 10,000 examples, and each example is a 28 by 28 image. But you flatten those images. 28 times 28 is 784. Sorry. So yeah. So the X has a shape of, if it's the validation data, it has a shape of 10,000 rows by 784 columns, right?
Right.
Okay. Now, lin1 is the mapping that maps that array, that input data into an embedding vector of length 50. So it multiplies the input array by a weights matrix that maps it into a column vector of length 50.
Mm-hmm. Okay, so it's taking all of those 10,000 by 784 and
yes,
and mapping that into something that has that is what by 50?
Yeah, it's a column vector. So you take the 10,000 by 784 input matrix, and then you multiply it by W1, which has to be 784 by 50.
Right.
So let me think.
So you're going to end up, I think, with 10,000 by 50. Is that right?
Yep.
Yeah, and that means for each example, you have an embedding vector of length 50 that you've mapped the image into it. You map the 784 pixel image into a 50 element embedding vector. Does that make sense?
Right.
Okay.
Yeah. And why, by the way, do you use the term embedding there?
It's I think it's from an earlier lecture. Let's not use that term if it's going to confuse you. All we're doing is we're mapping the 784 element input into a reduced dimension. You know, we're reducing its dimension to 50. You know, Jeremy chose that number out of a hat. He has a reason for choosing it, but you could have just as easily mapped it into 200 or a 25 or 20 or 10. You know, but he's
right.
So he's giving us 50 dimensions to represent that image. All right, and then the next step is just to apply this activation function element by element. So each of the elements get mapped by this ReLU activation function. So if we start with a 50 element vector for each example, then applying the ReLU to that 50 element vector will also give us a 50 element vector. So the output of this ReLU, layer is also 10,000 by 50. Right? All right, the next step is to map that 50 element vector into a single digit. And to accomplish that, we have to multiply it by another matrix that has a dimension of 50. So we're basically going to take the dot product of the 50 element vector with this 50 element weight W2 matrix, which is basically a vector, and that's going to give us a single element. Does that make sense? Okay. Yeah. Okay, so that's what's happening, and then well, that's why I say that lin2 actually gives you the prediction of the number. So lin2 should actually map directly of y hat. Right, y hat should be the digit, and so lin2 should map directly to y hat. But also, when you have all this stuff, you can compute the mean squared error. All right, so here we are. I didn't get as far as I wanted to. It's 9:48, and we've got like a few minutes to go because I wanna finish so that the next so that people can get to the next class in time. But let me go back to the notebook. Share the notebook. Fully connected. You're seeing the notebook now?
Yep.
Yes.
Yeah, okay. So now here's where we are. We got about halfway through this thing, and the hard part is all in front of us. So I'm sorry about that. We didn't get through as much of it as we wanted. But what he does is he basically defines this loss function. He defines the gradient. Sorry, he defines the loss function, a gradient of the loss function with respect to some input, and just basically writes this function. Then he writes the function to take the gradient of the ReLU. These terms are all the terms that come up in a chain rule, so you need them. You need the gradient of a linear function. And then once you've got those, basically those three pieces, you can now build a forward and backward pass. We already built the forward pass, but this is just building it again. But then the backward pass is here. You know, you get the gradient of the MSE, the gradient with respect to the first weight matrix, the gradient with respect to the ReLU, the gradient with respect to the second weight matrix. That's what this function is doing. Then we run it on the training data. And then we save these gradients for testing later, I guess. So he's basically just, I'm not sure how this .g thing works, but it's here. It's adding a property to these weights and biases. So I guess that's what it's doing. And then he uses clone. I guess that's the way that you copy a tensor so that you won't change its value by messing around with these things. All right. Now he says, since we've already figured out how to do this on our own, we get to use PyTorch. So now you can do the same thing with PyTorch. Then he defines just the forward pass with this function. And then he calculates the loss. I guess the output of the forward pass is just the MSE, the mean squared error. So now you run the forward pass and compute the loss function. And that's the end of the forward pass. The aim of the forward pass is to compute the loss function. Because the next steps is the backward pass where you're twiddling with the weights and biases in order to minimize the loss function. So here's the backward pass. And it's implemented in PyTorch already. So that's kind of cheating, but not really, because we've already implemented it ourselves up here in the forward and backward. So he's using the actual PyTorch function. And now he's testing the outputs of our method against the outputs of PyTorch's method. And remember, he has this test near, that is to see if these two are, that is the difference of these two are supposed to be close to 0, tolerance of 10 to the minus 3. That's what this test near function is doing. So you don't hear any complaints. That means that they all pass the test. The next part, yes.
I have a quick question for you.
Sure.
It's a notebook question. I had difficulty with test_near, and I just want to see if anyone else had difficulty with that passing, and just learn a little bit more about what's happening there. That wasn't successful for me.
Okay, I think I know why it wasn't successful. I think it's because you have to import. The very first step is you have to import from this thing. XNB01, that is the stuff that you created in Notebook 1. And I have Notebook 1 here, but my menu is hiding it from me. Let me see if I can. Yeah, so here's Notebook 1. And in Notebook 1, that's where he creates this test near function somewhere.
I think it's implemented in Notebook 2 itself.
Oh, it's implemented in Notebook 2? Okay.
Yeah, the other test is implemented in Notebook.
Oh, well, but does he use something? He uses something from Notebook 1, though, doesn't he?
Right, he does use. But I think if you command F test near, I think you should be able to find it here. Yeah,
so the problem is, your problem, that is the one who was asking me, your problem is probably that you weren't able to successfully import this the stuff from Notebook 1. Does that make sense to you?
It does. I did actually skip that part.
Aha, okay.
And I just got the MNIST data manually. Okay.
I see. Yeah, that's it. Because these notebooks in this course are constructed serially, so that to run each notebook, you have to have imported the result from the one before it. Okay, so I think that will solve your problem. You could post questions if you have trouble getting that implemented, and we'll try to answer that later on. Okay.
Thank you.
Yeah, you're welcome. Let's see. So where are we? We are back. We did all of this. We did all of this. We're in the backward pass. We're now in the refactoring part, and this is where it gets really, really a little bit hard to follow, because he's using, he's redoing everything by wrapping everything into these classes, and the advantage is that it really speeds things up. I think we had somewhere where he computed the time that it took to run this backward pass. The backward pass is the one that takes the most time. The forward pass is generally pretty quick. I'm trying to see where, oh well, I don't have time to look for it. Where we timed the backward pass the way we constructed it, the first way to do it, the foundations version. Now he's refactoring, and things substantially speed up from the way he refactors things. Well, okay, maybe there's still some speeding up to do. Even after this first round of refactoring, I have a note that it ran in 6 seconds, so it's pretty slow. Try that again, and it's slow. Yeah, it took 7 seconds to run it. So then he goes through a bunch of refactoring. I'm just going to run through this really quick, but the end result is it speeds up by a factor of 40, roughly. So with a time of 8 seconds, that's not practical. You can't run, you can't really test models and so on if you have to wait 8 seconds for every run, because it's going to do backward passes many times in a run. So in the training run, so you got to make it much faster, and that's what he's doing here. Let's see. I think I ran this on this. The forward pass is about the same as before, but the backward pass is substantially faster. It's much faster, speed up by a factor of 40 according to my notes. Okay, then he goes one step further. In this pass, he uses einsum somewhere right here. And then he says, well, we don't really need einsum because we have the native PyTorch matrix multiplication, so we'll use that. It doesn't speed up anymore. It's about the same. And then he does the test again. No complaint, so it worked. And then finally, he builds the final version of the model, and there it is. Computes the loss function, computes the backward pass, and there it is. And then the next step is to export this notebook in the Python script so you can use it in the next notebook. Okay, I'm going to leave now because I want people to have time to get to the next class if they need to. So I'm going to stop sharing. I'm going to end the meeting right now. Thank you all very much, and I'll see you next time.
Thank you, Joseph.